Hello everyone. Today we will be trying to solve this problem about van der Waals matrices, which are of this form. I usually like to solve problems without looking at them and then record it, but since I was not sure if I could even remotely do this, I started working on it. Here's my thought process that we will try to follow along, and I've solved more or less until the third. uh, which we will try to explain later. Okay, so the first step is read the problem and notice what's a van der Monte matrix. We have a first row of ones, and then each row is a geometric series with a different um, real number as the ratio. We have the first is one. And then we have this int, which is begin by adding minus x1 times the kth column to the k plus 1th column for each k until n. Well, not n, because then you wouldn't have a k plus 1 column, but up until the one we should be here. Okay, so here is where I started first, which is the decomposition of a determinant, which is the first element times the minor, which is not the matrix. I know it has a rigorous name, but I don't remember that. And then changing the sign depending on the position. But this did not really work out, and it was not following the hints, which I didn't read. So yeah, the first is to show that the determinant is the product, the symbol is product of all the differences of the ratios where the I don't know the name, the xi is greater than the xj in the position. It's like uh, yeah, mm, la, well, it doesn't really matter because it's very clear to see once you start working on it. So let's do that. I'm going to move all of this. Just 1 second. Uh, okay, and we can start working here. Now, the first element is doing this means for the first row you do minus x sub I times the kth column. Yeah, column, sorry, not rows, which would be all minus x sub I, and that I have to add to x sub I, so we would have um 1 1 1 1 da 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 da, and then minus x sub I. If you got x sub I times x sub and then x sub I x sub 1 minus x sub 1 is 0, and now you will have x sub 2 minus x sub 1, x sub 3 minus x sub 1, so on and so forth, and then x sub n minus x sub 1. And now for the next, x sub 1 times minus x sub 1 would be minus x sub 1 squared, so this will also be 0. And then all of this will go to 0, because since it's a geometric series, if you multiply by 0, then you get as by x sub I, by the ratio, you will get the next element, and if to the next element you subtract the prior, then times the ratio, you will get 0. Now, x sub 2 minus x sub 1, you will get minus x sub 2 x sub 1. And what do you subtract that from? To x sub 2 squared. And then for this, the same x sub 3 squared minus x sub 2, x sub 3 minus x sub 1. So x sub 3, x sub 1. And now for the next one, what do you have? You will have x sub 2 minus x sub 1. So you will have minus x sub 2 squared x sub 1. And what do you subtract that from? X sub 2 cubed. and here is the same, and for this is the same up until you reach x sub n, x sub 2, sorry, n minus 1, which you subtracted the previous to a like the to a lower power x sub 2 to the n minus 2 times x sub 1, and then the same for here, x sub 3 to the n minus 1 minus x sub 3 n minus 2 x sub 1 pa, 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 x sub n minus 1 minus x sub n minus 2 x sub 1. And you want the determinant of this, because since it's elementary row, well, not an elementary row operation, which also, but since it's a linear combination of columns, because it's x sub 1, which is a real number, times a column, and you add it to the no other column, then the determinant doesn't really change, because that's one of its properties. And now, if you do the minor decomposition of the determinant, you will notice that you will have 1 plus 0 times something plus 0 times something plus 0 times something. Therefore, the determinant will only be equal to the determinant of well, 1, because you go here, times the determinant of the this matrix here, the one that is not enclosed, like, yeah, if you know, fuck, sorry, and this. Now, what is this? Well, you will have x sub 2 minus x sub 1, x sub 2 squared minus x sub 2 x sub 1, so on, and then here is the same, and something like that, x sub 3 squared minus x sub 3 x sub 1. I think that you would imagine what's this like, up until x sub n, minus x sub 1, that, I. All right, now notice that you can take the common factor in here. In the next terms, you will have x2, like you will have x to the I minus x to the I minus 1 times x of 1. So you could take common factor the previous element. So you will have that this is equal to the determinant of x sub 2 minus x sub 1, x sub 2 times x sub 2 minus x sub 1, x sub x sub 2 squared times x sub 2 minus x sub 1, and the same for here, x sub 3, and you could keep going for every row. Now, if you look carefully, this is a common factor in this row. And by properties of the determinant, if you have a common factor among all as a row like this, it's the determinant is equal to the product times the determinant without this. For example, on a 2 by 2, if you've got 2 times 3 plus, and 2 times 4, 1, and 2, the determinant of this would be equal to the determinant of 2 times 2 times the determinant of 3, 4, 1, 2. Okay, so now instead of 2, we have x2 minus 1, x3 minus 1, x4 minus x1, and all of those. Since this, then this will give the product of this times this times this times this, the for all n. Then you will have that it's x sub 2 minus x sub 1 times x sub 3 minus x sub 1 times x sub 4 minus x sub 1, so on and so forth, up until x sub n minus x sub 1 times the determinant of almost the next van der Mon's matrix. Not quite, but it's also van der Mon's matrix because it's 1, 1, 1. since it's the common factors, times x2 squared, x2 n minus 1, xn minus 2, sorry, because it's one less. Look at that. In the third position, you've got uh, uh, mm, yes, sorry. Mm, this will end with xn minus 2, like you take common factor xn minus 2. So this will be x sub n minus 2. Otherwise, this would be an n times n minus 1, which is not true because we have taken uh, one row and one column. So this is an n times n minus 1 times n minus 1 matrix. Well, that's ugly. Okay. Now, this expression here, uh, it's the same as uh, saying the product, it's like the sum, but the products of i's greater than 1, because here we start with 2, 3, 4, 5, up until uh, x sub n, uh, yeah, up until n of x sub I minus x sub 1, which looks a lot like the question, like what we need to prove. It's not quite because we have a j here, but it seems like it's going all right when we follow this clue, times the determinant of another van der Mon's matrix of one less dimension, n minus 1, with x2 squared, and x2 n minus 2. That's a pan. Now, though, we can make the same process and as we have done here, and do uh, one uh, just, but now instead of using x1 we use x2, so we'll have that it's the product of I greater than 1 up to n of the determinant of 1 1 1 1 0 0 zeros, and here we'll have x3 minus x2, x3 times x3 minus x2, and so on and so forth. And then we can do this recursively. Well, sorry, here I forgot this. X sub I, x sub I minus x sub 1 times this. And now, following this, we'll have that this is equal to the product of I greater than 1 of n of x sub I minus x sub 2 times the product of I greater than 2, because now we're starting with 2, up until n of x sub I minus x sub 2 times the determinant of the next van der Mon's matrix 1 1 1 1, x sub 3, x sub 3 squared, so on, x sub 4, up until x sub n, and up to x sub n minus 3. So we've been decreasing this matrix dimension. Therefore, there's probably a more rigorous way to prove this, but I'm not that good yet. So we will try to work with this way, which is uh, looking at this, it's increasing by 1. It makes sense that it increases by 1 because you're doing the same and you're starting with one more. So this is equal to the product of I greater than 1 of x sub I minus x sub 1 times the product of I greater than 2 up until n, all of this, times x sub I minus x sub 1, x sub 2 times the products of I greater than 3 of x sub I minus x sub 3, and so on and so forth, up until we have the product of I is greater than n minus 1 up until n of x sub I minus x sub n minus 1. But if you look at this, um, we have that this 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 uh, mm, this product is difference of difference product of differences all have that the first element's index is greater than the other index, and this is true for all. And we have that they range from this point, from the 3 up until the end, all of them up until the end. So this is equivalent to saying the product of i's greater than j up until n, like n uh, greater than or equal to ij of x sub I minus x sub j, which is what we were asked. This is the solution to the first question. It's true that it's not as rigorous as I would like it. There's probably ways to do it by induction, and uh, yeah, like we're using induction on the range of the matrix, and then I think this is follows from by definition, but I'm not that good. There's probably a lot of better people for doing that, which do that. Now, deduce that v of n is invertible if and only if the x of I are distinct. Okay, so we can use our little formula that we've shown, not really proven, uh, from the first question, and have here we got that the determinant of v sub n is the greater than j up to n of x sub I minus x sub j. So if we had x sub I equals x sub k for x sub I different or I is different than k, then it's true. If they're different, then the indexes must be I greater than k or I less than k because they're different. It doesn't really matter for our proof. Well, for our proof, if I is greater than k, then there exists x sub I minus x sub k in this product. So, well, let's do it more formally. If I is greater than k, then there the product of I greater than j do have x sub I minus x sub k. Well, mm, better yet, it will be x sub I minus x sub k times the product of I greater than j such that I is different from k of x sub I minus x sub j. Okay, this uh, I'm messing around too much. We all know that since these are both equal, then this will be 0 because this is equal to 0 and this is just a product of terms. And then if a matrix A is invertible if and only if and only if no sorry if and only if or if and only if the determinant of A is different from 0. If they're equal, then it's 0. So if they're equal, they're not invertible, which is literally the question. X sub A is invertible if and only if X sub I are distinct. Um, I don't know if they asked you for something more, but using this property of the determinant, then it follows quite straightforwardly that this property holds. Now let's do x sub 0, x sub y. Okay, Lagrange interpolation. Let x sub 0 up to x sub n, y sub 0 up of y to n be real numbers with x sub I distinct, so that there is a unique polynomial p of x of degree n or less, such that p of x sub I equals y sub I for each I in between 0 and n. Finding such p of x is called Lagrangian interpolation. I don't know how to pronounce that. Okay, so I learned this in class, so it's more easy to me, but it's not as hard as you might believe. Okay, so we want a polynomial where if you plug in x sub I, you get a, y sub I. Okay, uh, then this would be easy if you define p of x sub I is equal to y sub I. Like p of x for any x is y sub I. However, if you try to make this for more, like if you want p of x sub uh, p of x sub 2 equal y of 2, then this polynomial doesn't work. Then what we want to make is a polynomial. Well, mm, it's not necessary. Like what we will do at first, it's a function where uh, we will have 0 at every point, but when we reach x sub I, we jump to y sub I. And otherwise, it's equal to 0 because then if you add all of these polynomials of x sub, I don't know, x sub k, and then y sub k, since you will have zeros in here for the first one, if you add them at those specific points, you will have y sub k. Okay. Now, how do you make this? Well, the best way to do this is to have a product of zeros, but right in this point is this is a positive number or it's not 0 because then you will only have to multiply y sub I by the result. Okay, so we want a product, and for that product, there's you want this point is special. We want that if this point is if the point is different than this one, it's 0. So uh, for any point, uh, uh, sorry, j. Okay, this is any point x sub j. Now, if you do this polynomial, uh, well, this is more like this: x minus x sub I for uh, Wait, sorry. Um, okay, okay, yeah, yeah, yeah. Since it's not like we don't want infinitely many points, uh, these are limited. So there's um some x sub j. Uh, these are the points we want. This would be this x sub k, this sub x sub f, and then y sub m. We just want that at this point, this function is zero. So this graph is honestly not quite good. It's more like uh, at any of these points, it will go, this point is what we want. Then for the next, it will go to zero. Then maybe it will do something like that, then goes to zero back at this point, and something like that for it to be a polynomial. Okay. Um, this is a product where for any point different than zero, because if I is equal to j, this would give um, zero, and we cannot divide by zero. And now, how does this work? Okay, let's think about this. It's um, x sub x minus x sub I times x minus x sub I. Okay, no, I'm so sorry. No, this is not an I, it's a j. Yeah, and let's see why. Okay, if you've got well, if you got x sub i's, and here x sub j, or x sub 1 minus x sub I, x sub 2 minus x sub I, let's suppose I is equal to 4, for example. So this would be x sub 4 and x sub 4. Now we have, if you plug in, and this will continue up until n. If you plug in x sub 1, then you will have um, x sub 1 minus x sub 4, which you would not know if it's 0 or not. You cannot guarantee it. Might be, it might not. Uh, it's it's probably not gonna be. Either way. Then, however, if you put x sub a, you will have x sub a here, which would be x sub 1, x sub 2, and so on and so forth. Um, Now, if you plug in x sub 1, this term will be 0. And since everything is a product, everything else will be 0. If you plug in x sub 2, this will be 0. So the same follows. However, now let's consider that this will go, and then you will have x minus x sub 4 times um, mm, mm, mm. No, sorry, you will not have this. You will not have an x minus 4 term, because this term is not included here. However, since the x sub i's are all different, are distinct, as is established um, in the in the question, x sub I are distinct. Then, wait, oops, uh, then you have the following. None of these terms are 0. And then if you plug in x sub I, so x sub 4, you will have x sub 4 minus x sub 1 over x sub 1 minus x sub 4. This is the first term. Now the next term. X sub 4 minus x sub 1 times x sub 2, sorry. X sub 2 minus x sub 4. Okay, I'm realizing that this will give negative, so it's better to either change the x sub I or the x sub j, so you will have the same x sub 4 minus x sub 1. So let's make this I and this j times x sub 4 minus x sub 3 over x sub 4 minus x sub 3, and then we will change this to make it proper. And then since these terms are different than 0, then this will be equal to 1 times 1 times 1 times 1. So if we consider only this polynomial, you will have a polynomial where for every term it's equal to 0, except for when p of xi, which is equal to 1. If the element is between um, x sub I, like it's not defined in x sub j's points, then you don't really know how much it will be. It will depend on the point. So yeah, it will be more like this. Uh, a polynomial that you don't know the behavior between the points you want, but at certain points you're certain that it will be either a 0 or a 1. However, you don't want a 1, you want the value y sub I. Then if you multiply by the term here, y sub I, let's make it in a different color even, y sub I, then when all of these are ones, then you will have that p of x sub I is equal to y sub I. And this is the first step that you want. Now you want to make the final polynomial that we will call capital P is of x, uh, such that it's not only one at one point. Well, y sub I at one point, which is this. You want it to be a certain value at every point you define. So you want this polynomial to be here, but this you want that this behaves like this, but then that it goes to here, and then it goes to here, and so on. Now though, you know how to make polynomials where at this specific point they're 0. So if you add two polynomials, if you think about this other polynomial, for example, where here it's 0, then at this point it's this, and then at the next point it's 0. If you add green and white, in between you don't know what you will get. But at this specific point, you have 0 plus the value. So that will give the value. And now green plus white. At this other point, you will get that the white 0 because it's different from the point you want, but the other it's y sub k. Therefore, the addition of these two will give you a polynomial that is y sub I at x sub I, y sub k at x sub k, and 0 at everything else. This should be like this. If you consider the addition of only white and because 0 plus 0 is 0. And there's the important fact. If you add a set of these polynomials, you will get another polynomial that matches the description you want. Therefore, it's the addition of the polynomials I different than j. Sorry, different than j up to n of um, x sub uh, x minus x sub I times x sub j minus x sub I. This is each polynomial is a polynomial for a certain x sub I, but you want for all x sub i's, so you will have for I equal 1 up to n. Then for x sub I, uh, oh yeah, and this is y sub I because it's the value you want. Otherwise, this would give 1. And this is the answer. And now, there's a certain property that the polynomial had to match, which was of degree n or less. Okay, what's the degree of this polynomial? This is n minus 1 because you've got all the endpoints, x times a, a, um, a simple factor of n, well, a simple factor of x times another factor of x, n minus 1 times because there are endpoints and you don't count the case where there I is equal to j. So this is of degree n minus 1. And then if you add polynomials of a certain degree, the degree doesn't change. If you add, like, you take the degree of the greatest. So if you add a bunch of x of n minus 1 plus x of n minus 2 plus x of n plus 3, then the degree of this polynomial will be n plus 3. So since all of these are n minus 1, the degree of this polynomial is less than or equal to n minus 1. And that's the answer for the first one. Now, let's keep going for the, oh, you, nope. Uh, okay, let's go for the last one, which I did not do yet, but it's determine a p of x when y sub 0 is equal to 1 and y sub I is equal to 0 for I greater than or equal to 1. Okay, here they're not saying that it has to be a polynomial, but let's assume that because then you could define a piecewise function such that it matches this. But it's pretty obvious that we want to continue with the previews. So I greater than or equal to 1. So it's a series. We have mm, okay, so since we only need to care about 1 point, y sub 0, we don't really need to, and its value is 1, so we will have I different than 0. Of x minus x sub I think, over x sub j minus x sub I. However, I'm not sure how, like, this does not have a limit. It's for all i's greater than or equal to 1. They're all natural numbers. Mm, I think it's only this, but this is not polynomial because it's degree, infinite degree per se. Like, it's not exactly a polynomial. How would you do this? Wait, uh, and y sub I equals 0. Well, this would be I then, and this would be zeros. Sorry. Here it would the previous j is now an I, and the I is a 0. So I'm pretty sure this is gonna work, but I'm not sure. Let's check it. I think there's the solution posted. Mm, 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 mm. Oh, mm, not this. Okay, I have not found the solution per se, but I think this is probably right. I mean, considering this exercise, there's really no restriction that doesn't say you can define this such that phi of 0 is equal to 1, y sub I is equal to 0 for I greater than or equal to 0, and uh, no, 1, sorry. So I'm guessing this is alright, and then this is also alright. If anyone knows the answer, please post it. I will gladly read it. And if anyone has any instructions or help that they could give, I'm really open for it because I'm not really that good as you have all probably seen. So thank you and have a nice day.